Okay.
It's kind of too close.
Oh no! Okay. See how that goes. All right. So number, is that all right?
There's just no head. It's funny.
All right, cool. Number 23 looks like this. Integral negative infinity to infinity. Squared over 9 plus 6. All right, so this is exactly what I'm talking about. They're going to start throwing all these combinations of stuff in there. What's kind of a first possible idea here? And I really want you to get a feel for how this works. Is there a function in there whose derivative is in there?
It could be.
Could be, exactly. That is the correct answer. Because, I mean, obviously if I let u equal the bottom, that's never going to work because there's not an x to the fifth in there, which would be the derivative of this, right? What is x squared the derivative of, though?
3x.
No.
The derivative.
What is x squared the derivative of? Something x cubed, basically, right? And do I have an x cubed in there? Yes, I do.
X cubed squared.
Exactly.
Wait, can you say that one more time?
So, from the very beginning, I mean, really, can I do trig sum from the very beginning?
No.
No, because this is a sixth power. There's no identities that involve sixth powers directly, right? So I can't really use trig sub directly. I can't let u equal the whole thing. So, I mean, I then look to see what there is free. What's free? And x squared is free. X squared dx. What would that be the derivative of then? X cubed. Then I think, okay, how can I rewrite something to have an x cubed? And there is an x cubed.
Oh.
Right? This is x cubed squared.
Okay.
So now what do you want to let u equal?
3x.
X cubed. So if I let u equal x cubed, what's du?
3x.
And there's the x squared. I can have a 3 show up easy enough,
Oh,
right?
okay.
Then you'll be left with something that looks interesting, right? Then you have a couple options of where to go. Let's go ahead and bring the limit idea in here. And you've got here now, well, basically it's going to be infinity of it, isn't it? U over, not u, but du 9 plus u squared, right?
Okay, I see.
Now, if you wanted to, you could either play with that a little bit. It's directly related to a derivative of a trig type thing, or you could use trig substitution on there, right? Now a trig sub will work because I got a squared thing plus 9. I can actually do a trig sub.
That was the inverse.
There you go. Yeah. So again, I don't know how much you guys had to memorize in Calc 1, but that is directly related to the derivative of inverse tangent, right? Okay. And then you just keep going.
It's because I had the solutions manual and they did that. I just wasn't sure why they did
That's why.
that. Okay.
You start to realize that, let me think if I can come up with this off the, so if I had a, I don't know. So same idea, if I had this situation, you can see how this would be similar, right? It's really the same situation. I have an x cubed, whose derivative would be out there. So that's what you're trying to do. You're always trying, for u sub, that's what you always try first if it's not just a direct integration, right? That's definitely not just a direct integration. U sub, but you have a lot more flexibility than you originally think. Because that's not just x to the 6th, that's x squared cubed or x cubed squared. You got a lot more flexibility there. And then on this one, so if you let, same thing, let u equal x cubed, du is 3x squared. So I get the square root of u squared plus 7 du, and then I can do, that'd be kind of an ugly trig sub, but too bad for us. Right? What trig sub would you use on this?
Tangent.
Tangent, and what would be the coefficient? What would be the coefficient of the tangent?
Running from x to the
Square root of 7.
Yeah, square root of 7. Get in there. Tangent. Blah, blah, blah. Do you guys start to see? I mean, you have with anything that's related to substitution. The whole idea of, well, if you say u is x minus 1, then x is u plus 1. That was the first, like, oh shit, I didn't know we were allowed to do that. Well, of course you are. Just stupid substitution. I just want to substitute all the x crap legally with u crap, right? And any way I could do that is fine. And this is not just x is 6, it's x cubed squared, blah, blah, blah. So I have a lot more hidden there than I could just see. There's a lot more in there that I could use. All right. And what was the other one? 25? Oh, that one just kind of screams at you what to do, really.
Let Ellen.
Yeah, you got to let u. So 25 looks like this here. And what's the e to infinity, of course. I mean, it's just screaming at you what to do here, right? I hope. Because the derivative of ln is 1 over x. There's a 1 over x in there, and there's an ln in there, hey, right? So you know exactly what you have to do with this. Yeah. Okay. And you just replace the infinities with the limit as t goes to infinity, or if there's something inside that's got a problem with 3, let t go to 3, that kind of stuff, right? The integration step is the same, and then you apply the limit at the very end. So it's really not any new work. You still integrate the same way we did before. It's just the last step is you throw an infinity in, or you throw a 3 in, or whatever the problem spot is. Okay. Cool. So anything else from chapter 7 before we get into chapter 11? Which, of course, makes sense. After 7, you, of course, go to chapter 11. It only makes sense. All right. So I've already kind of referenced chapter 11 before, especially when I did stuff like integrating from negative infinity to infinity. We had that whole discussion last time about how that's... Remind me now, because I was tutoring somebody about this too. We did talk a little bit about that, where the areas cancel until you go to infinity, because they have to separately converge. So if the limit from negative infinity to a, from a to infinity, they have to separately converge. You're not allowed to just go ahead and say, well, they cancel if I go out from this. No. You've got to separately converge. So we're going to eventually get to the point in chapter 11 where we're talking about the same exact idea. And we can get a little deeper into why you have to be so careful.
Us to separate them?
Yeah, so remember last time we were talking about the integral of an odd function? So if an integral of an odd function, like x cubed, from negative 4 to 4, I have no work to do, really. What's the answer to that? 0, because x cubed has the same amount of area down here as it does up there, right? What is that, Jeff? All right, same amount of area from here, but this is negative 4, to here is 4, right? So those areas, of course, cancel. Because separately, the areas are finite. Whereas the minute I start doing this, separately, the areas on each side would actually be infinite. So technically, by definition, that integral does not converge, right? Which really kind of sits uneasily on me a little bit still too, to tell you honestly, because it's just purely a definition. But when you see it in the sequence thing, it'll make it a little bit easier to take, I think. Okay. So hopefully you guys at least understand why that looks like it should not be confusing, and it actually kind of is. That does not exist, right? It doesn't converge. Okay. You look so excited to be here. I love it. So let me start us off nice here. We're going to get into chapter 11. Chapter 11 is all about sequences and series. We're also going to discuss something called mathematical induction, which sounds like a weird hazing process or something, or sounds like a painful thing. Has anybody ever heard of math induction? Yes? Math induction is a stupid, powerful proof method. It's one of my favorite in the world, but it's also takes a bit of a click moment for you guys to understand it. It's kind of like, we'll get there. So we'll talk about math induction, and it's really kick-ass cool. It helps you solve a lot of things easily that otherwise would be not so easy. So let me give us a few examples here. If I wrote this here, I'm not going to give us the full, let's do it like this, n greater than or equal to 1. Now that little n, whenever I use a symbol n in mathematics, very, very often, most of the time, I mean that is what kind of number?
Rational. Regular. Real number.
Okay, real, but more specifically?
Natural number.
Natural numbers. That's why I use the letter n. N for natural numbers, right? So this would be 1, 2, 3, 4. Okay? So I have the first term, the second term, the third term, so forth. So can somebody tell me what would the first term be in this sequence?
1/5, 1/5.
Yeah, exactly. So if n equals 1, I get 1 over 1 plus 4, 5. If n equals 2, I get
1 over 6. Or 1/3.
2 over 6, 1/3. N equals 3,
Yada, yada, yada.
3 over 7, right? Can somebody tell me real quick, are these getting smaller or larger, or what do you think is going to happen with this sequence in the long run?
It's going to get smaller.
Can equal 1.
It's going to approach 1, right? You guys, and you can meld stuff that you already know together with this. You already know how to do this from pre-calculus, right? If this was a function, if this was f of x equals x over x plus 4, when he talked about like horizontal asymptotes and all that kind of crap, what situation is it in? The powers of the x's are the same, therefore its asymptote, its limit in this case, would be the ratio of the coefficients. Does that sound at all familiar? Or you do the whole thing where you divide by the biggest power. You guys remember doing this? 4 over x, and what does 4 over x do as x gets really big? So of course you end up with 1, right? So the whole idea of the three situations, so the top power is larger, so it goes to infinity, or they're the same, so it goes to the ratio, or the bottom power is bigger, so of course it goes to 0, because the bottom gets bigger quicker, right? That's really an offshoot of doing that work. So I'd rather not do that work. I could just think about the three situations, right, for that kind of a thing. So if I have a polynomial over a polynomial, that's easy. No problem there at all. So if you kept writing these out, these should be approaching